Sample problem is 14.04. Floating buoyancy and the density. In figure 14-11, a block of the density low 800 kilogram per cubic meter floats face down in the fluid of density low F 1200 kilogram per cubic meter. Block has the height h 6 centimeter. First question, by what depth h is the block submerged? Number B, if the block is held fully submerged and then released, what is magnitude of its acceleration? So let's take a look at the first case. The buoyant force is same as gravitational force applied to the fluid, which is replaced by that block. So number A, buoyant force is the effective force or effective mass in case that the amount of the volume is replaced by the box. The amount of volume of the box is replaced by the fluid. So here the mf is the mass of the fluid displaced by the submerged portion. So number one, the fluid floating requires that the upward buoyant force on the block match the downward gravitational force on the block. So if the buoyant force now is upward and gravitational force downward, so if these two forces are equivalent and they are balanced, then that make this object, the block, actually floats inside of this submerged on this fluid. And buoyant force is equal to the weight mfg of the fluid displaced by the submerged portion of the block. So that should be low equals mass over v, that is density, and the mass should be therefore the density of fluid times volume of fluid. So from that, F buoyant force mf times g should be low F, the volume g, actually volume F times the g. So here this volume F is the block's face length. So here that should be L times W. Here L is the length, the face length of the block. And this is width that showed, so that is like a volume. So you replace it, then that should be low F L W. Oh, here's actually H. There should be H too. H, the height, times G. So similarly, gravitational force Fg is M times G. Here M is low, and that should be volume V, and that should be also the G. So that low, the V volume is L W H. That's volume of the object, the block. So if you replace the V with that, then low, that should be low L W H G. So floating block is stationary. That means the upward force and downward force, they're stay in balance. So if you apply the Newton's second law along the y-axis vertical direction, then that force should be equal to 0. because they're not moving downward or moving upward, or there's no up and down movement. So that indicating that the force from gravitation and the buoyant force is stay in balance. From that, F net y vertical direction is MAY. That should be equal to 0. So if you plug that the two forces into this Newton's second law, then that is F buoyant force minus gravity, Fg should be m times AY, and the AY equals 0. So that is m times 0 should be equal to 0. So from that, if you plugged buoyant force and the gravitational force into this formula, then that should be low F L W H G minus low L W capital H Z should be equal to 0. From that, you can find the relationship between the height of box and the submerged portion of the box in this liquid, the water. So from this one, that LH just cancel out of first and second terms, and G also too. So the H submerged part of this box in this the fluid is ratio between these two different material, the fluid and the box, times height of box. So that the density of the box is 800 kilogram per cubic meter, and the density of fluid is 1200 kilogram per cubic meter, and height of this box is what, 6 centimeter, right? So from that, the height of submerged portion of this box in equilibrium of their movement should be 4 centimeter. And now let's take a look at the acceleration. How much acceleration so number B, the block is held fully submerged, then released. What is magnitude of acceleration? You've just pressed this box complete submerged into this fluid, and you just let go of the box. Then the box will just push it back against the buoyant force. So that start to have some sort of acceleration from the rest. So we gotta just find out the magnitude of its acceleration from that condition.